Ooh, but let's not forget our arbitrary constant, right? Really easy to prove. Just take the derivative of this thing, right? I want to prove it. I go f prime x. And remember, capital F. You got to be real careful. Like I can have a tendency to get a little lazy and make my capital F's look like lowercase. So be careful. This is going to be n plus 1, right? Because this is just x. These are just all constants, right? This is going to be x to the n plus 1 minus 1 over n plus 1. This n plus 1 was just along for the ride, and then plus 0 because the constant goes away. Cancel, cancel. Last I checked, x to the n plus 1 minus 1 is just equal to x to the n. Yay, QED. I'm so smart. Okay, now let's talk about how to get rid of that constant. What do you need? So let's start with a simple one. Remember f of x equal to x squared, and we ended up with an antiderivative of x cubed thirds plus c. Now think about what this is. These are both functions, right? And we've had enough discovery time with functions to hopefully you can visualize what this is. The problem is that x cubed thirds plus c is a family of functions that looks like this. I end up with an uncountably infinite number because c can be anything, and there's an uncountably infinite number of real numbers, right? So this is the family of x cubed thirds plus c. We'll call this the family. So think about this. If I want to be able to solve for c, notice that all of these pass through at the c value, because when x is 0, y is c. I'm actually going to stick a y equals. Y is going to be c every single time. So all of these guys pass through at whatever the c is. If I'm going to be able to solve for c, all right, to solve for c, what do I need? Think about it. To solve for c, what do I need? Well, this is an equation with how many variables in it? It's got 1, 2, 3 variables. So if I'm going to be able to solve for c, I need what? I need a point. I need a point. X, comma, y, right? There's 3 variables to solve for c. I need an x and a y. That's pretty easy to do, right? Which makes sense. Think about it this way. If you give me a point that I know that this function passes through, let's say that it's that point right there. All right, I don't care what it is. We'll call that x naught comma y naught as in some sort of value. Okay, then I know that there is a function that passes through that point, and only one function. There's only one. It's a unique function. Now this point is often referred to as an initial value. So it's a value that's given to us initially to be able to play. Okay, now watch how easy. Remember Newton's laws of motion? You also hear this referred to as rectilinear motion, which sounds a little funny to say. You also hear them as the ballistics equations, things like that. All right, think about this. If I drop an object off a building, off a cliff, with, now let's assume that drop means that I can sort of chuck it too if I wanted to, with initial velocity, we'll call this v naught, and a height of h naught. So this is what Newton did. And a height of h naught come up with the formulas, I guess it'd be formulae, wouldn't it, for velocity and position. Okay? That's what we're going to do right now. That's what, as soon as Newton figured out that, supposedly the apocryphal claim that an apple fell out of a tree and smacked him on the head, right? He started figuring out these laws of motion. Well, think about it. What do we know? All that I know is that the acceleration of gravity, I'm going to say a of t, is going to be, well, it's going to be negative 9.8 meters per second squared. That's all I knew. True? However, What do we know about the derivative of velocity? It's acceleration, which implies I know, don't we know, that v of t is the antiderivative. Because if the derivative of velocity is acceleration, then v of t has to be the antiderivative of acceleration, right? Well, that's cool. So don't I know that a of t, don't I know that v of t is equal to, the antiderivative of a constant is just going to be negative 9.8 t, right? A constant becomes a linear term, plus c. Well, what do I know? The initial velocity, what does that mean? Initial velocity means that v of 0 equals v naught. True? So that implies that v of 0 equals negative 9.8 times 0, that's t, see, I just, wherever I saw t, I stuck a 0 in, right? Plus c, and that equals v naught. Well, those cancel. It appears as though c equals v naught. Guess what? We have our velocity equation, which is negative 9.8 t plus v naught. You've probably seen it in your physics class. Well, what do we know about position? All right, so I can call this h of t. In other words, what's the height of this object, right? Well, it is the antiderivative of what? Velocity. Because if I take the derivative of something's position, I get velocity. We've already played with that. So what does that imply? It implies h of t equals, now we got to be careful here, the antiderivative of negative 9.8. Oh, by the way, why is it negative 9.8? Well, think about it. If I drop an object, its height is decreasing. So acceleration is having a negative effect on the height. That's why it's negative rather than positive. So hopefully you can see that this becomes negative 4.9 t squared. Right? If I take the derivative, in your head you should constantly be taking antiderivatives and derivatives, etc., right? Plus v naught t, remember this guy was just a constant, whatever it was, whether I chucked the ball or the rock straight down or I dropped it. All right, whatever that initial velocity was when it came out of my hand is what goes there, and then plus. Now we got to be careful here. This is going to seem a little pedantic, a little inane. However, if I write a c here, it implies that this c and this c are the same. Now I'm guessing that you can see that this c and this c are not going to be the same. So what I do is I just stick a little subscript 1 there, and that tells me that these two c's are different. Well, wait a sec. Look at what we got here. We have an initial height of h naught, which implies I know that h of 0 equals h naught, right? Well, h of 0 equals negative 4.9 times 0 squared, wherever I see a t, stick a 0, plus v naught times 0 plus c1, which is what I want to solve for, and I know that h of 0 equals h naught, the initial height. Guess what? Those go away. c1 equals h naught, which implies h of t equals negative 4.9 t squared plus v naught t plus h naught. Ta-da! You've seen these before. These are Newton's laws of motion. That's where he came up with them. Isn't that awesome? Very, very cool. And look at this. Check it out for your Algebra 2, just to sort of put a bow on the whole thing before I let you guys go. We know that this is of the form ax squared plus bx plus c. Look at it. A t squared plus b t plus c. This thing's quadratic. Think about it. If I drop an object off of the roof, it's going to do something. If this is t and this is h, it's going to do that. It's an upside down parabola. I know that this point right here is 0, h naught, and down she goes. Now I have something where I can compute the velocity at any time t and the height at any time t. Awesome. Hope you enjoyed that. Congratulations, you've made it through basically differential calculus. Enjoy, and I'll see you tomorrow.